Hello, everybody. I hope that you can all hear me. Adam, if you can just confirm that you can hear me.
Yes.
Good.
Nice and
Perfect.
clear.
Thank you. So, hello, my name is Theodore. I'm the director of IDEA StatiCa UK. And I would like to welcome you to Connection Wednesdays, our weekly online training for IDEA StatiCa. A unique software that allows you to analyze and design in minutes any type of still connection according to the Eurocode or the American code. So we're going to start. People are still joining, but we're going to start anyway. So if you are already a user, or if you are trialing IDEA StatiCa, or you're just interested to know more about this breakthrough technology, we believe that this series of webinars will help you and give you, let's say, a deeper insight on the software. So before I introduce our speakers for today, I just wanted to mention a couple of things about GoToWebinar for anyone that hasn't used it yet. It's a software tool that we're using for the webinar. So at the right side of your screen, you're going to see a control panel, which you see that you're already muted. So for practical reasons, by default, we have mute everyone. But you also see a space that you can enter any questions that you might have during the webinar. So feel free to do that at any time, and we will try to answer them as we go along. So our speakers for today are Adam and Kostis. We're going to present you the 4 examples that we have prepared for you. So first example is a general 3D joint that will be presented by Adam. It's a quite complex connection, as you can see, that contains also a custom cross-section. And this is the first time in this series of webinars that we're going to show how to create a custom cross-section. Through this example, we're going to show you the whole process of modeling, loading, and design of the connection so that you can get a full overview of the workflow. Next, we are going to switch to Kostis, who is going to show you how to perform stiffness analysis. This is one of the most powerful features of our software, and Kostis will explain you a little bit about the theory behind it and the practical use of this analysis type. After that, we are going to go into the beam link section of our webinar, and Adam is going to show you the link with TEKLA structures and how you can save a lot of time by importing the joint into IDEA StatiCa. We are going to finish this set of examples with a link with SCIA Engineer, a structural analysis software. So as always, we're going to show one CAD and one analysis software link. And this is also, as you can see, a quite complex connection. After that, we're going to have some time to answer all of your questions. In case we don't have the time to answer all of them, we'll make sure that we answer them through an email. So don't worry about not hearing your question answered. You will still receive an answer after that. After the webinar, you will immediately be directed into a survey, an online survey. It's just 3 questions, not much. So it wouldn't take more than 10-15 seconds to fill it. So kindly take the survey. It will help us a lot. We are also recording this webinar, so in 3 days you're gonna also receive the link to the recorded video in case you want to go through it again. If you have never used IDEA StatiCa, of course, you are more than welcome to download our free trial version. It's a 2 weeks trial from ideastatica.com. And we're absolutely sure that you're going to be impressed by the ease of use and the potential of our software. According to the feedback that we have until now, almost all of our trial users within a couple of days, even one sometimes, they're able to design really complex connections. So please go ahead and check it out. And as mentioned before, this is a series of webinars that we do every Wednesday. So these will run until the end of July. And we're actually doing 2 sessions every Wednesday in the morning and the afternoon. So make sure you register also for the next ones, as we always show different examples and features of the software. So we want to show as much as we can. We're going to do a break during August. So we're going to start again from September with many more exciting stuff. So let's get started. I'll give the screen to Adam to start with the first example.
All right.
So Adam, I'm just
hello, everybody.
make a presenter.
Yeah, thank you. Hello, everyone, once again. Greetings to next Wednesday with IDEA StatiCa. Hope you're fine. We're going through together this rather complex joint complex in geometry. So this is how it's going to look at the end. So let's start directly. Just start IDEA StatiCa and create a new project. And I'll just pick some of the predefined geometry which I'm going to change right now directly. So I have some geometry here, and I will start by composing or creating the geometry for the column. So this is the member SL, it's the column, and I will now choose here the tab Welded Composed, and here I'm going to choose the general steel cross-section icon. So by this, by clicking here, the cross-section editor opens, and this is a tool for composing a custom cross-sections that are not in the library, not ordinary. So first we get a tab here to actually like input the first shape that would form our final cross-section. So I will start with an I section and select here HEP 600. So this is the first part, and I'm just continue by adding another one. And for the second one, I will select a T section. That's a cut of a I section, and change the shape to HEP 500. All right, so there's something here already, and I will make a copy of this one by clicking here. So I have 2 of them, and now I have to process it a little bit, and this is being done in this tab. So I have those 3 shapes here, so I'll change the master component of those 2 T sections to the first one. So they will be connected to the I section. And now some numbers here appeared, and those are like the connection points. This is used for this 2 rows. The master point is set for 0 here. So you can see it here, it's 1, 2, 3, 7, 8, 9, and along the web there are other numbers. 0 is the center point of the I section. So I will leave 0 here. And now I change the number on the T section. It has its own numbers as well. The insert points, as you can see here, 1, 2, 3, 4, 6, 7, 9, and so on. So I will change it to 8, which is at the bottom of the T section. I will do this for both of the T sections. So they just moved upwards. and they are connected to the I section. And now I just have to rotate and move it a little bit, so I do it by this. Input 90 degrees and minus 90 degrees. And since it's still overlapping here, I'll just move them by the thickness of the web of the I section. So now I'm actually done with composing the general cross-section that is looking like this. And you can check if it's created in the right way by going to result here in this editor, and you can see the tau mx value displayed, and this is showing you also the mesh and if the connection is being done correctly, and you can see that the flow of the stress here is just right, is correct, so that's fine, and we're done with that. So just click OK here, and it's here. As you can see, the column has the general cross-section. So you can play with that, create all kinds of shapes and cross-sections, and you can even import a drawing from a CAD software of the cross-section into the editor and just input it directly if you like. All right, so I'll just change the length of the column here to 600 to have it shorter, and continue with modifying and the parameters of the geometry and adding more members here. So for the member B1, I'll change the cross-section now just from the library. I don't need to use any more composed cross-sections, so I'll just continue with the library. So this one, and I will tilt it a little bit to the right, as you can see. Then I continue with B2, change the cross-section to HAP 180, and I want to rotate it minus 6 degrees, so it's all in the same direction, right? Then I add another member, set the cross-section from the list, which is already here, and I'll just change the direction so it's like this, and to have it connected with the P1, I put here 6 degrees as a pitch and 0 for rotation. So it's now like this. And I will add just one diagonal, for which I will choose an L section of 100 to 8. So it appeared here, and again I will change the direction and have minus 40 here of the pitch, and I want to have it on the right side, so I'll input 0. So that's it. We're done with the geometry. This is looking fine, so let's go to next step, which is the load effects. So this is empty here, and since I like really the feature that we can import the forces, so I'm going to do that. You can always input the forces manually here, but I'd like to import it from an Excel sheet, which is much more comfortable. So you basically just copy and paste the forces here, and it's there in the tab, and you can check it in the window as well. All right, that's for the load effects. Let's go to design, and we will start with the first operation, with the cut operation. And I will actually use a cut to lengthen the column. So you do this by selecting a member to the column, which is SL, and we will cut or actually lengthen the column by the member B1. For this one, we only change this cutting plane to farther. So now it's actually lengthened the column, and I would like to have some offset here as well. So I will have some space for the welding and the plate for the connection and so on. So like this. And now, just to save time, I will skip the other operations that you have seen before, and we will see in other webinars as well. So I have another file prepared here with the operations done. So I'll just briefly go through it. You know, I have the end plates for both the beams here, end plate 1 and plate 2. I have the fin plate to connect the this beam B2 to the main column web, and I have a gusset plate to connect the diagonal with 1 bolt. Actually, this reminded me that I forgot to tell you one important thing. Since we create a connection with 1 bolt that is typical for diagonals, we have to think of the model type of the diagonal, and we change it here in the geometry. So I select the diagonal, and here's the model type that you can read the information here. So if I change to this one, to the last one, it allows only axial forces and shear forces to get into this member, and it prevents from during the calculation to the additional extra bending moments from the eccentricity, as you can see, is eccentric, to occur there, and that would really like change the results and you know, be different from the reality how it's working. So this is really important thing. All right. So let's get back to design. This is actually done. So we just proceed to check and click calculate and let the iteration process start and run. And in the meantime, I'd like to show you again our resource center. This is our webpage, ideastatica.com. And if you go to the resources section and click to IDEA StatiCa Steel, you've got a lot of information about the software in general. Basically find everything here, and you can find here also the tutorials, which is sometimes pretty handy, and you can find also the general 3D join that I'm showing you right now, the step-by-step tutorial you can go through on your own. It's all described here, all the information. You can also download the file of the project to go through it. All right, so let's get back to the results. It's already calculated. So this is what you're seeing is the basic display that comes out after calculation that we call the traffic light, and it shows you quickly whether the joint is all right or if it doesn't fit the code criteria. So this basically shows you the gray colored parts of the joint or the beams, tells you that the value or the percentage of the usage that this part can bear is under 60%. The green one is 60 to 95% of usage of the plate or the member, and then the orange, you can see the bolt here. This is a 95 to 100, and what is over 100 that is not here actually is then in a red color, and this didn't fit the criteria of the code. So that's it, and just briefly go through other displays we have. This shows you the plastic strains that are in the joint. You can see the equivalent stress along the whole joint, how the stress is distributed, and you can turn on the bolt forces. You will see the arrows here. If you click on the arrow, it directly shows you the tab here on the left with the bolts. You can see every bolt here listed in the tab with all the numbers, all the values of the forces, and you can even open the equations here to go through all the equations according to the code. All is described here. The same for welds and so on. And you can also turn on the mesh here, see how the model is meshed, and see the deformed shaped, or even have it like over ratioed to see the deformation, deformed shape of the joint. So that's it from me for the first example, and now I'm giving presenter to Kostis, who's going to show you a stiffness analysis. So I'll see you in a bit.
So hello everybody. As Adam told before, in this part of the webinar, I will show you how to calculate the stiffness of a connection. For this, I will start a new project, and I will use the Frame 2D wizard to create a new connection. I will use this configuration, and I will just use the provided cross sections for this example. Now, let's go to the design tree item, and let's use the template button in order to skip modeling. So I will use template, and I will apply a template. Here you can see that from the topology of my members, the software shows some proposals for connections. So for this example, I have already prepared a template, which is ST1, which I will apply to my connection. Okay, IDEA asks to choose a bolt size, so I will go with a 10.9 bolt grade and choose an M20 bolt. I will press OK. And here you can see that the template is applied. Okay, modeling is done. Now let's add some loads. I will go to the load effects tree item, and here I will load the beam with the same load. So both beams will have a load of minus 20 kilonewtons at a moment of 40 kilonewton meters. And we can see that our connection is ready to be solved. I will go to the check, and here I will press calculate just to make sure that our model solves and passes all checks before we can proceed with the stiffness analysis. As you can see, model passes checks. From here, we need to go to the project items where I need to change my analysis type to stiffness analysis. A word of caution here is that if for some reason you need to maintain the results from the previous analysis, you can always copy this project item and work on the copy. For this webinar, I will work on this project item. So let's change the analysis type to stiffness. And let's go back to the geometry. And here, the important thing is to select which member is the analyzed one. The analyzed is the member whose connection will be classified against stiffness. For this type of analysis, it is important to have set the correct theoretical lengths. For a beam, this value is the beam span, which is defined as the center-to-center distance between the supporting columns. So, for beam B1, which is the analyzed, let's leave the default value of 6, go to the check tree item, and from here we can calculate and perform the stiffness analysis. So while the software works, let's go and discuss some basic concepts for stiffness analysis. So why is stiffness analysis so important? When we solve our global model, we make assumptions for the boundary conditions of the beams. So let's say that we have a full strength model which produces the top moment diagram. If we use a connection that is semi-rigid or worst pinned, we can see at the rest of the diagrams that there is a redistribution of the moment which may lead to a failure not to the connection but to the actual member in the ultimate limit state. So for this, Eurocode requires stiffness classification of the connection. This classification is done according to the requirements of paragraph 5.2.2. There, the initial rotational stiffness of the joint is determined, and this initial rotational stiffness is compared to classification boundaries. So let's go back to IDEA connection and see how this is done. In IDEA connection, our connection is already solved. I will skip the overview of the checks since Adam presented all these details, and I will go straight to the rotational stiffness tab. So here we can see a table of results, and these results presented as a diagram. So I will start explaining the diagram a little bit. I will start from top to bottom. First, the top line is the member's bending resistance. Next, we have the joint resistance, and then we have 2/3 of that value. So this value is used for the definition of the initial stiffness of the joint, which is represented by a line starting at the axis origin to this point, noted with a light green label. We can clearly see that this line is between the stiffness boundaries defined by the code, which are shown as a blue line for the pinned boundary and an orange line for the rigid boundary. As a result, our connection is classified as semi-rigid. Of course, you can see all these results in this table, and from the outcome of our classification, this means that we need to go back to our analysis model and replace the rotation boundary condition with a spring whose value is the calculated initial stiffness. So this concludes this part of my presentation, and I will move the presenter again to Adam to show you the TEKLA link. So
All right, let's get back to TEKLA link from the TEKLA software to IDEA StatiCa. So I have prepared one example of such a joint. Well, quite a complex joint in TEKLA. So let's get to export from TEKLA to IDEA. This is the tab for the link, which is integrated by installation of IDEA StatiCa. It integrates into TEKLA and other softwares as well. So here on the ribbon, you just choose whether European or American code you want to run. So I'll just type, just click on the European. The window with the feature opens, and now we just have to select a node on the connection, like this one. And next step, we select the beams of the connection, like this. Press spacebar, and then we select the items of the connection, such as plates, bolts, welds, and so on, and press spacebar. Now we wait just about 1, 2, 3 seconds, depending on the computer, and a window opens and asks us to save the project. So just I save it to whatever, and IDEA StatiCa opens. And now we can see the connection, the joint imported in IDEA. It's all there. So I'll first go to geometry. There are all the members, and here's actually nothing to do. It's all there, nothing to add. The only thing I will change here is you can see the boundaries. They are by default set on this plate or this member that's connected to the main column. So probably it would be better to have it on the column. So I will just find which one is the column. And this is the member 3. So I'll just click bearing member here. And now I have the boundaries on the column. All right. Then I move to load effects, which is obviously clear here. There's nothing here from TEKLA. So again, I have an Excel sheet prepared with the forces. I have some 3 beams and loads for those 3 beams. So I will import those forces. I have 3 beams, and here I have 6 members. So this is something you have to take care. Where are you actually putting or pasting the forces? So it's better to take a look which one is which one. This is member 4, 5, 6. These ones I want to load. So it's here at the end of the tab. So I'll just put it here like this. All right, so just first step is to check the members when we are importing from Excel sheet. All right, it's there. Second thing maybe to check here by doing this is if we have it in the right order, right? So we have it in an order. So this is one row and another row and third row. So if we have it in the same order, so we can just see in the 3D display. So we just go, it's member 4 and has 100. So yeah, this is looking good. So that's it for the load effects in the design. There's also nothing to add. It's all there from the TEKLA export, all the bolts, welds, and so on. So the last thing is just to run the calculation. So just let it run. And well, just to fill the time, I can show you. So I'll switch back to the resource center on our web page. And here in the list of tutorials, you can also find a TEKLA link. And there are 2 examples that you can go through. There's one that we were showing in the first Connection Wednesday, and another one, an example from a steel hall that you can also go through and download the files for that here with the TEKLA project as well. So that's it. And the calculation is done here. And again, we can see the default display with the traffic lights to see whether it's all right or not. And according to this, we can just simply change anything in the design. Change, for example, any of the bolt grade and so on. And just check it once again with the improved design. So this is it. Now, since you go to design, it deletes the results. So I have the same file open here as well, just to show you or remind you about one thing that we have the reports here. 1 line, 1 page, or detailed. Those are 3 options. The most used or most interesting is the detailed report, where you can manually or by yourself set what would you like to have there, and here you can see what is there actually printed. You can see all the checks, all the tabs for all the members, for the plates. You can see some pictures here as well, and checks for bolts, check for welds, and so on. And you can of course print it out, print it to PDF, or save it and process it in a Word software. So it's all open for you to work with that. So that was it. And this was the TEKLA link. And I'm going to switch to Kostis again, who's going to show you another nice link. All right.
Okay, thank you, Adam. So here I have SCIA Engineer opened. We have to note that this is the latest version of SCIA Engineer 17, which has a really improved beam link with IDEA StatiCa. And here we have a real structure from a real project. What I would like to show you is that for presentation purposes, I have created about 200 linear combinations that I will export to IDEA StatiCa. So I have created a result class, and I have added all these combinations in this result class so that I can export them at once. So how do we communicate with IDEA StatiCa? First, the structure needs to be solved, which is something that I have already done. And then we have to go to the steel category, where we can see the IDEA StatiCa connection feature. Let me change the representation of the model a little bit. Let's open the nodes. So how do we communicate with IDEA StatiCa? Here I go and select joint input, and the software asks to define a name for my connection. For the moment, I will leave the default. I will press OK, and I will pick one really complex connection. So let's say this one, this node. I will press Escape. and the software creates a label that shows my node. Next, I have to go to the check. I will change the type of load to the classes, and I will use the design class, which contains the 200 linear combinations. So I will export to IDEA StatiCa connection, choose the defined connection, and press escape. So the software starts working, and it will take some time since it needs to pass 200 combinations to IDEA connection. So IDEA connection opened, and here we can see that we have all members passed through the BIM link with their cross sections and of course their load effects. Just let me show you a little bit. So all loads are here. I will go back to the geometry, and the only thing that might be necessary is, is to go and change the length of some members. So that I have a size that is appropriate for the connection that I want to model. So this is it. I will not model this connection from scratch. I will again go to the design, pick the templates, and apply a template which I have created before. So the software recognizes the topology of the connection, and I can apply the already created connection. I will use this default bold grade. And the template is applied. Let me zoom a little bit to show you how complex this is. Now, what's interesting is that if we model, solve, and save our connection, SCIA engineer will keep all these manufacturing operations in the model. In order to demonstrate this, I will close this connection without solving, and I will change SCIA engineer to another model that has this connection already solved and saved. So here I can go back to the steel category. I will go back to IDEA StatiCa connection, press the check button, and I will export the connection to IDEA StatiCa. I will select the label and press escape. Here you can see that SCIA engineer created a connection with all the manufacturing operations already applied. So you can have your joint fully modeled and saved in SCIA engineer, and in case that loading changes in the initial model, then you don't have to create your joint from the scratch again. But you can always check an already designed connection. So with this, I conclude this part of the presentation, and we will answer your questions. So Theodore.
Yes, thank you, Kostis. I will just switch back to my screen. Okay, so yeah, I just wanted to emphasize a little bit what Kostis has showed. So regarding templates, so we chose to show this feature in this webinar because it's a really powerful feature that it's often overlooked by users, and it allows you to save an incredible amount of time. So in IDEA StatiCa, someone can create, let's say, a number of different configurations. So as you go along and you are dealing with new projects, you can always go back and just create a new connection without having to create all these different manufacturings operations one by one. So it's a really nice feature. So please, if you're using IDEA StatiCa, just go ahead and try this out. So just a reminder, as I mentioned earlier, you're going to receive a short survey at the end, so please make sure you fill this out. The recording, again, you're going to be receiving that in 3 days, and of course, if you want to go and try our software, just go to ideastatica.com and make a request about the trial. So let's go ahead and start with the questions. We don't have a lot of time, so okay, so let me just go through them. And first we have a question. It's about the length, so Adam can answer that. Was changing the length to 600 for visual reasons only? Is it only for visual reasons, or does that have an impact on the design? So Adam, if you can please answer that.
Yes. I will just take the presenter and I'll show you. I was going through the questions now, and in the meantime I went to our FAQ section in the Resource Center. And this FAQ sections is based on the IDEA users' questions that they are sending to us, and we are picking continuously the most important and most interesting, and we process it, and then we add it here to this list. And there's also answer for this kind of question. Is this FAQ? What's the correct length of member? I changed the length to 600, or you saw also Kostis changing the length of some members with the SCIA example. This has two reasons. One reason is just for the spatial reasons. If you have a connection like this, or you have a big gusset plate, and if you have the length just too short, there's not enough space for the gusset plate connection or so on. All right. And the other one, the second reason is that you don't want have the length too long, or like this on the picture on the left side, because then if you calculate in IDEA the extra added moments or extra added forces from the analysis will occur there, and they could a bit, you know, change the results or like that. So we have like a recommendation for this, and by default it is the length of the member is set to be 2 or 3 times the width of the cross section. So like this, and you can read yourself more information about it here in the FAQ. So this was about the length.
All right, thank you, Adam. Just keep your mic on because the next one is for you as well.
All right.
Can you outline when to apply the forces at the distance X in the load case tab? This is still a bit gray area.
All right. So I'll show you where it is in IDEA, what we are talking about. We were talking about the length, which is here, that's obvious, and now we're talking about the load position, or the position of forces. So we go to load effects, and here there's a list in every load effect, and you can position the force either in node, in bolts, or some position that you can then set here by yourself. That's the X position on the axis of the member. So this is handy. You can also go through, we have it also in the FAQ actually. This is here how to define load position. So we have information here about this and you can go through. This is by default, it's on the node. This is just the basic setting that you use always in the analysis software. So you position the forces in the node. But then when you're checking a connection, a joint, sometimes you have maybe, no, this is not the best example, but if you have a connection with bolts, like a fin plate, that the bolts are going through the plate from the side, then you will, if you leave the setting at the node, you will get a moment, a bending moment in the bolt, which is not realistic and it's not according to the calculation process normally. So what you do is that you switch to bolts, and you can switch to wireframe here to see it, but unfortunately this is not a good example. So I would have to spend some time to create another connection. But you can check it here by changing to wireframe. If you change the bolts, then the force moves a bit along the beam, and then you will get the zero bending moment in the bolts in the fin plate according to real behavior of the connection. So this is it. And then there's a third option, which is position, and you can do it manually by yourself, just as you wish to try or model some situation on the joint. Just move the force wherever along the beam. So this is there. So that's
all right.
it.
Thank you, Adam. Next, we had a question about a tube connection, a CHS tubes knee connection, how we can model it. As we don't have a lot of time to show this connection, we are going to send you an email after that, after the webinar, so we're going to send you some detailed, let's say, instructions about that. So next question is, does the software take into account prying forces? So Kostis, can you answer that, please?
Yes, of course. Okay.
So I will make you a presenter. Yeah.
Yes, I have to take the presenter. Okay. Let me open the FAQ. So we have already this answered also in the FAQ. Just let me search. It is in the check and report. Yes, it's here. So no, it is in here. So the software takes into account prying forces because it models end plates with a contact element. So you can see from this example here how the prying forces are taken into account and increase the bolt forces when we increase the size of the end plate. So in this example, the end plate is 10 millimeters. So the bolt resultant is 296 kilonewtons, while the applied force is 200 kilonewtons. And if we thicken the plate to 40 millimeters, you can see that the bolt resultant has lowered. This is due to the prying forces. We have less prying forces here. So please check our FAQ in our resources center and have a look at this example.
All right, Kostis, the next one is for SCIA, so it's for you. Can we choose what combinations or load cases we want to import, we want to export from SCIA? I think you more or less showed that, but can you just please go through that again?
Okay, so let me activate one of my models here. So there are many ways to do that, but the one that comes to mind right now is I will create a new result class. Let's call it test. I will delete all ULS combinations, and I will just add these two. I will press OK. I will then go back to still. Oh, I'm sorry, but I will have to reopen this because we lost. Okay, I will do it with this. We lost the solution, so we could not export the results. So I will go here and create the result class in question. Let's say test. Okay, close this, go back to still, and then I will check the joint, and here the type of load I have classes, and I will use the result class that I have just made. I select test, export to IDEA StatiCa and the joint. I press escape, and I'm waiting for IDEA connection. You will notice that it's a little bit faster because we have less combinations to pass through. So if we go to load effects, you can see that we have these two combinations that I have just selected. So this is it. Okay.
All right. Okay, I think that's answers exactly the question. So since we're running out of time, let's just go through quickly one last question. Adam, if you please answer that. Can we use preloaded bolts?
Mm-hmm. Sure, we can. I'll show you where you set it. It's in the design, and if you have some bolted connection,
first of all, I will just make you a presenter.
Oh, sorry. I'm sorry.
Yeah, we'll still see because this screen.
Yeah. I'm sorry. So now you can see, right?
Yeah.
So if you go to design, and we select some bolt connection, for example, this one. Then here at the bottom, there's an option for shear force transfer. And if you have bearing or bearing tension shear, that means standard bolts. And if you change the friction, then you are using the preloaded bolts. So this is how it works. And I bet you can find this information in the FAQ as well.
Okay. All right. Thank you. So let's wrap it up, and I will just switch to my screen. Okay, so I hope you have found all this really interesting. So again, please join us for the next Wednesday webinar. So we're gonna do, actually we have already uploaded the registration form. So it's, if you go to ideastatica.com webinars, you will see that the next webinar will be on the 12th of July. So there we have already chosen the examples that we're going to show you. So you can see we're going to show about joint design resistance, a bolted plate, a splice connection, plate to plate, and some links with advanced design and advanced steel. So you can just register here. So I think that's about it. So thank you very much for joining. We'll be really happy to see you in one of our next webinars. And please, if you have any question that you might want to ask after the webinar, you can always send us an email at HelpDesk or at IDEAStatiCa.com. Also, if you want to see some of your examples presented in one of our next webinars, you can also send that to us. So thank you very much and see you in the next webinar.
Bye-bye.
Bye.